Alright, hello, welcome to this AQA electrochemistry basics tutorial. This has mainly been made for the benefit of my year 13 students who haven't been in lessons, but also you could use it if you're not in this school. Hopefully it'll help you learn some of the basics of electrochemistry. Now what I don't promise here is that you will have a deep understanding of electrochemistry, but what you will get from this is a set of skills that allow you to answer pretty much any electrochemistry question. So firstly, I'm going to show you what electrochemistry questions look like in exams. They look like this. You have some sort of half equation. You can tell it's a half equation because it's got electrons in, balanced with electrons, and they have some voltages known as standard electrode potentials. So you flip over this page, there's some more questions. That's how you tell you're dealing with an electrochemistry question. So what I'm going to do, so here they are, there's loads of them. So what I'm going to do, I'm going to talk through some simple principles of electrochemistry. I won't get through the whole lot now, but this will give you some basic skills. And the skills we're going to be touching on today is how to draw a cell, how to do something called standard cell notation, how to calculate Ecell, otherwise known as EMF, and also when we're drawing the cell, some of the conditions required. This is not going to be a slick video, it's not scripted, it's just me going through what I've been doing in my last few lessons. Right, so first things first. I'm going to do a little bit of theory. It won't be in too much depth because you don't need to be able to recall this bit. Okay, so I haven't got any chemicals out with me. But I want you to imagine now that you've got a beaker. We're going to be drawing a lot of beakers soon, and next to it you have another beaker. Now into one beaker you're going to put a strip of metal, into the other beaker you're going to put another strip of metal. Now if you put some copper into some copper 2+ solution, what will happen here is there will be an equilibrium set up between the metal copper and the copper 2+ aqueous. So what you'll have is your copper 2+ aqueous. As soon as you dip this copper in, some of that copper 2+ aqueous will turn into copper. Some of the copper will turn into copper 2+ aqueous. And actually this is the most useful way to think about it. Some of the copper will go into solution. Effectively it will dissolve and at the same time become copper 2+ ions. So if some of the copper goes into solution and becomes copper 2+, some electrons will be released. You may already notice that I'm drawing it with the electrons on this side. So as a gain of electrons, even though I've described it as some of the copper will go into solution. This is one of our first electrochemistry conventions. All of the equations, those half equations you will see in exams, are written as a gain of electrons. Now we've got another beaker over here. Imagine that I put some zinc into some Zn2+ solution. What you'll have is some of the zinc will turn into Zn2+. And as it does, it will release some electrons. And again, you might be looking at your screen, scratching your head, saying, why did you draw it that way? And the answer to you simply is because that is the way that we draw it. All right? So in this beaker, some zinc will turn into Zn2+ and release some electrons. Some copper will turn into copper 2+ and release some electrons. The electrons that are released will sit on the surface of the metal. Now, if you think back or use your general knowledge about chemistry, I hope you remember that copper is less reactive than zinc. So because copper is not very reactive, only a small amount of it will turn into copper 2+, which means you'll only have a few electrons on the surface. I'm going to represent that as 2 electrons. Of course, it'll be in many millions in real life, but we're just going to represent it as 2. The zinc, I hope you realise, is more reactive than copper, so you could imagine, couldn't you, that more zinc will go into solution. So that means if more zinc becomes zinc 2+, there will be more electrons on the surface of the zinc. So maybe I'll represent that as 4 electrons. Okay. The theory then is that there's now some electrons sitting on the surface of the copper and there's some electrons sitting on the surface of the zinc. So if we connect these with a wire, and a little voltmeter there, and a wire, a little crocodile clip on the top, I hope you're thinking that the electrons could run along the wire and they would run from the zinc side, which is comparatively more negative because of the electrons, to the more positive copper. And you are right, apart from the fact that this clearly isn't a complete circuit. But you are right in the idea that the electrons could flow through a wire to here. So we get electron flow from negative to positive. The only thing is, if you're making an electrochemical cell, you also need to complete the circuit by putting what is called a salt bridge. Now, until you've seen one of these in action, you might think, oh, it sounds very theoretical and very difficult. You literally soak some paper or some cloth, or you can have a tube full of ionic solution. So you soak a piece of paper or cloth in ionic solution, saturated ionic solution, which means lots and lots of ions in there. Now, typically we use KNO3, potassium nitrate, saturated. So what you've got inside this salt bridge, you've got K plus ions and NO3 minus ions. So negatives are going around the circuit this way, and I think I've got this right in saying, so negative ions will move this way and positive ions will move this way, and they can carry the charge between the solutions. The point is, you need to know that you've got to have a salt bridge to make this thing work, and it's going to have a saturated potassium nitrate solution. Now, it doesn't have to be potassium nitrate. It could be sodium chloride, it could be potassium chloride, it could be iron sulfate, as long as it's ionic. The rule about it is, just be careful, the chemicals, the ions that you choose in your salt bridge, be careful that they don't react with the ions that you dip them in the beaker. So an example might be, if you have some Ag plus ions in a beaker, you don't want to have Cl minus ions in your salt bridge, because that will make a white precipitate of AgCl. For example, KNO3 is the classic go-to ionic salt bridge because it doesn't, a simple way of saying it is, the K plus and the NO3 minus very rarely react adversely with any other solutions. They make soluble products. So just remember it, you need a salt bridge, KNO3 minus. Alright, so all of that was this setup to say that if you have more electrons on the surface of one metal than on another, you will get a current flowing and you will get a voltage being read here. Now, wouldn't it be nice to know, or wouldn't it be nice if scientists had basically worked out how many electrons are on the surface and how many electrons on the surface? And the point of it is, they have, and it's called the electrochemical series of standard electrode potentials. So if you have a look down this list, and hopefully if you're in my class you've been sent this. Alright, this is a list of half equations, all written with the electrons on this side. It doesn't mean that they always go this way. It means that it can go this way as well, but they're always written with the electrons on this side, so they are written as gaining electrons. And if you remember, reduction is gain, they are written as reductions. So we find the two that we've done. We had zinc in zinc 2+, and it says that it has an electrode potential, an E standard of minus 0.76. So what we do on here is go minus 0.76 volts. I will tell you where these numbers come from later on. And you see the copper, I'm looking for copper and copper 2+. Copper, well that's copper and copper plus, not that one. Copper and copper 2+, plus 0.34, plus 0.34. And so earlier on we said copper will have fewer electrons, and these numbers back this up. This doesn't mean that copper has actually got positive, like it's got protons on it. All these numbers, they are relative to each other. This means that the zinc has got more electrons, it is more negative than the copper. So the difference between the copper and the zinc is the difference between these voltages. What this means, if this is a battery, that is obviously the more negative, so that'll be the negative terminal, and this is the positive terminal, and electrons will flow here. So I've used my electrochemical series, and it tells me that zinc is here and copper is here. Okay, you got that? So, some terminology. Each one of these beakers with some metal in is known as a half cell. This is a half cell, and together we have drawn a cell, otherwise known as an electrochemical cell. So together they are a cell. To make a cell, you need a wire and you need a salt bridge. A half cell and a half cell. You can call this a Cu2+/Cu half cell, and you can call this a Zn2+/Zn half cell. That way round, please, the same way as you would read it on the half equation. Alright, so there is your basic introduction, and now I'm going to tell you what skills you need in the exam. So firstly, you need to be able to draw these. Secondly, you need to know that for these numbers to be used, you have to have very standard conditions. Because if you see here, they're called standard electrode potentials. So it says that they're all at 298 Kelvin, but also all solutions are 1 mole per decimeter cubed. So if I was making notes on this video, which I think you should be, you need to write down solutions 1 mole per decimeter cubed, temperature 298 Kelvin. Saltbridge, KNO3. These are all marks you can get in the exam. Alright. The next thing to do, so we know how to draw that, the next thing I said we were going to do is how do you do a standard cell notation. Now, if I wanted to communicate to another chemist that I'd made this cell in my lab, well, I could draw it like that, but surely there must be an easier way to communicate that. And you're right, it's called a standard cell notation. And you can imagine that this would have been quite easy to do on an old typewriter or even by email, and just a very quick shorthand way of communicating this information. So what we do, we go double line down the middle, which represents the salt bridge. On this side, I'm going to put the Cu half cell. And what we do, I want to say that I've got copper and copper 2+. What we do, I'm going to put the copper 2+ next to the salt bridge, and I'm going to put the copper next to it. I'm going to write the state symbols in like that. The reason I put the copper 2+ here is because it has an oxidation state of +2 and the copper has an oxidation state of 0. And the rule is, out of everything in that beaker, the species with the most positive oxidation state, so this is +2 and this is 0, the species with the most positive oxidation state touches the salt bridge. So on this side, it would be Zn2+, because that's touching the salt bridge, and Zn here, solid, aqueous. The final little touch, solid and aqueous are what we call in different phases. You can think about that now as being different states. It's not exactly the same, but it'll do for now. Solid and aqueous are different states or different phases, so we put a line down the middle to show that there is a boundary between them. And I'm going to put a line there. And this is your completed standard cell notation. It tells somebody that you've got a salt bridge in the middle, that your right-hand electrode, as we're looking at it, your right-hand electrode has got copper 2+ and copper, and your left-hand electrode has got zinc and zinc 2+. The general convention here, and this is where I'm going to introduce the most important 2 letters for this topic, is that you put the positive on the right. You put the more positive half cell on the right. Okay, so PR, you've got to remember that. So if you remember that this was plus 0.34, that's why I've put this one on the right, and this was minus 0.76, so I put it on the left. If you arrange it so that you've put the most positive on the right, and you've put the most positive oxidation state touching the salt bridge, it reveals a very special thing. It actually tells you what happens in this cell. If you've drawn this correctly, it tells you that this chemical will turn into this, and this will turn into this. So in this case, it tells you that if you run this battery, this cell, sorry, the zinc will turn into zinc 2+. So this little strip of zinc metal will disappear. The zinc 2+ concentration will rise. The copper 2+ will turn into copper. So this copper electrode will get bigger. It tells you exactly what happens. This turns into this turns into this. Of course, look very carefully. If you didn't put these in the right order, this whole thing wouldn't work, so you have to do it correctly. Alright. So this leads me to another reason why PR is really good. It means put the positive on the right when you're doing a cell notation, but it also tells you that the more positive electrode, this one, is where reduction happens. If you look here, the Cu2+, to turn into Cu, must gain electrons. That is reduction. The zinc on the left hand side turns into Zn2+, and to do that it must lose electrons. That is oxidation. So positive is put on the right, and positive is where reduction happens. PR. Alright, if you're looking at this now and you're thinking, I can't remember what a half equation is, stop the video, go and look that up. Go back to your notes from last year and look at half equations and find out what reduction and oxidation is, because literally there's no point you carrying on with this video if you don't know the difference between reduction and oxidation. remembering that oxidation is loss of electrons and reduction is gain. Alright, let's look at a different situation now. We're going to get faster because we're 15 minutes in and I want my lunch, to be honest. Alright, so what I'd like you to do, please, draw 2 beakers. That's my drawing beaker song. We're going to put a strip of metal in this one and a strip of metal in this one. We're going to connect them with a voltmeter. We're going to connect them with a voltmeter. We're going to put some liquid there, and we're going to do a salt bridge, which has got saturated potassium nitrate in. Electrons are going to flow through the wires. Ions are going to flow through the salt bridge. Alright, now then, let's choose some metals. Let's choose tin, that's SN, and tin 2+ in one beaker, and nickel 2+ in another. So these two. Okay, which one do you draw where? Well, I know that you put the positive on the right. So the more positive out of these is tin. So I'm going to put my SN2+ N here. So that's some tin, SN, and that's dipped in SN2+, and I know that's got a value of minus 0.14. And this has got a value over here of minus 0.26. So this is nickel 2+ in nickel. Okay, minus 0.26. Got those values off here. What this means, there's more electrons on the surface of this nickel than there are on the surface of this tin. That makes this the negative electrode, this the positive electrode. Electrons are going to flow like that. Okay. How do you represent this standard? 1, 2, double line. Tin 2+ in tin. We're going to put the tin 2+ there. We're going to put the tin there. You're not going to forget your AQ. You're not going to forget your solid. You're going to put a solid line between them. You're going to go Ni 2+ there. You're going to put a line. You're going to go Ni solid there. Aqueous there, solid there. What does this tell you? Well, it tells you your nickel is going to turn into nickel 2+ and your tin 2+ is going to turn into your tin. So the examiner might say, what's going to happen to the mass of tin when this cell is discharged? They would say that, which means when it runs. What's going to happen to the mass of tin? You're going to make more tin. The mass is going to go up. Yay! You've got to remember to put the positive on the right, and you've got to remember that positive is where reduction happens. So you could say, write a half equation for what happens at the positive electrode. Write a half equation for what happens at the positive electrode. Positive electrode is this one. I know that the SN2+ will turn into SN. Write a half equation plus 2 electrons. Write a half equation for what happens at the negative electrode. I know that the nickel turns into Ni2+. And it will do that like this. The examiner might then say, write an overall equation for what happens. Well, overall equation is a combination of these two. 2 electrons are gained, 2 electrons are lost, so they're going to cancel out. So you'd write SN2+ will react with nickel to make SN plus nickel 2+. And that's the overall reaction for what's happening in the battery, even though these two chemicals never actually meet. There's the cool thing, just stop and pause for a minute. What I'm saying is if you've got a different metal, a metal in 2 different oxidation states on one side, and a metal in 2 different oxidation states in 2 separate beakers, you will get electrons that travel down this wire and you will generate a current, you will generate electricity. This is how batteries are worked. Companies like Duracell, though, realise it's quite impractical to make beakers next to each other, so they managed to pack all of these little setups like this into a nice little battery like that. If you cut one of these things open, you will see something that acts like a salt bridge. You will see something that acts like an electrode, and you will get lots of solutions in there containing metal ions. It's all in there. Duracell, they do it all the time. Obviously, this is how we would do it in a lab. Okay? Right, the last thing they do that I realised I didn't do for the last one is how do you work out the voltage for any sort of cell? Well, the rule is the Ecell, which is the overall voltage, is the difference between this number, which we're going to call the, what's it say here, standard electrode potential. The standard electrode potential of the right, this little symbol here means standard, that means 298 degrees C and 1 mole per decimeter cubed. The Ecell equals E right minus E left. So in this case it means minus 0.14 Sorry about that, I ran out of space on my phone, so I've managed to free up a little bit of space, and I've got 4 minutes left to do some more, and then I'll run out of phone space completely. So what I was saying is, if you want to calculate Ecell, you do E right minus E left. So in this case, you would do the electrode potential, think of these keywords, of the right, minus 0.14, minus 0.26 volts. This gives you the difference, known as the potential difference, or the EMF, or the Ecell, of 0.12. It's literally the difference between these two numbers. I then went on to say, because I hadn't realised that my phone had died, on the first one that we did, if you go E right minus E left, E right is the most positive one, plus 0.34, so you write that in there, minus E left, which is minus 0.76. You get a voltage of 1.10 volts. Next, I'm going to draw another one. I've got 3 minutes left. Okay, so beaker, beaker, metal in beaker, salt bridge, potassium nitrate, salt bridge. Drawn carefully, please. I really am running out of time. Voltmeter, voltmeter. Let's choose a different one this time. Aluminium in Al3+, and this time I'm going to go below the line. I'm going to go silver and silver plus. That's a strip of silver in Ag+. Okay, the voltages, the electrode potentials, silver and silver plus is plus 0.8 volts, which is why I put it on the right. Aluminium and aluminium plus, I'm reading that off here, it's minus 1.68 volts. You can just about see it on the screen there. Alright, so I put the positive on the right, because remember, positive on the right and positive is where reduction happens. Double line down the middle, Ag plus, Ag, line, state symbols, aqueous, solid, Al3+, aqueous, Al, solid. Next thing that we do is we go, this will turn into this will turn into this. Your silver's you're going to get more silver. The concentration of silver plus will go down. You could write half equations for these. The Ag plus will turn into Ag. The Al will turn into Al3+. This will do this by gaining an electron. This will do this by losing 3 electrons. If you wanted to combine these together, there's 3 electrons here, 1 electron here, so you need to multiply everything in the top half equation by 3, and the overall equation will be 3 Ag pluses plus Al makes 3 Ags plus Al3+. Gosh, I'm running out of time quickly. That's the overall equation. Ecell equals E right minus E left equals 0.8 minus 1.68. That's the difference between positive 0.8 and minus 1.68. That is 2.48 volts. Okay, you getting the idea? That's how you do it. Alright, you draw the cell, you'll get the numbers in the exam. If you wanted to do the standard cell notation, you will put the positive on the right, the negative on the left. You use a double line for a salt bridge. You need to know what a salt bridge is made of. You need to know that these numbers that we're putting in, 0.8 and 1.68, are done at 298 Kelvin and 1 mole per decimeter cubed. And then Ecell down here is how you calculate it there. Ecell is E right minus E left. Right, this is just to the one person at home who didn't come to the lessons. We've got a minute left of this video. What I would like them to do, so if you're watching this, your initials are RP, you should be watching this at home. Can you do task 5 please, redox basics, working through some half equations. I would like you to do that, it's going to be very useful to you. And then following on from that, let's have a little look. Nothing yet. Okay, so watch that video, do task 5, and I'll get back to you soon. Goodbye.